So is the screen visible?
Yes, sir.
Okay. So let me know if you have any query related to the lecture of yesterday and previous lectures. Otherwise, we will start something new, which is one of the major aspects, the transformation of variable. Actually, we have done the transformation of variables, but here we will have a formula to transfer from PDF to PDF. Okay, especially. So we need to know that, and also we need to know how does it come. But fundamental idea, how does it come? It is same as you do the variable transformation when you do integration. Okay, so the method of substitution as you do, it will be the similar thing. Here also, it comes in a very nice form, although the statement of the theorem is not so straightforward. I'll try to make it precise. Yes, so this is the theorem that we are going to see today. Yeah, I hope you can read it. Already the PDF file is with you. So this theorem that let phi be a strictly monotonic function on interval a to b with range phi of I, and it is differentiable with differentiable inverse. Okay. And also we assume that x be a continuous valued random variable such that the PDF exists, and the PDF takes value 0 if it doesn't belongs to I. So that means the PDF is completely supported on the interval a to b. Okay. Then if you define y equals to phi of x, and the density function of y is given by g on the range phi of I is given by y, g of y is f of phi inverse y. That means the inverse function, it will be fx eventually, and the derivative of the inverse function. So it is nothing with absolute value. So this absolute value is the most important thing here, because you see that it is a PDF. So PDF cannot take negative value. So either it can be 0 or it can be positive. So that is the whole idea. How does it come? So to see the theorem, we can prove it very easily. It will not be difficult. Uh, the main idea is this: you have to consider two cases separately, that they are either monotonically strictly increasing function or monotonically strictly decreasing function. So for these two cases, you have to handle separately, but end of the day, you will come up with same expression. Whether it is increasing function or whether it is decreasing function, it doesn't matter. It will come up with the same expression, that the density of y is f of phi inverse y, derivative of the inverse function with absolute value. So let us consider the situation. Then okay. So I'm just in short, I am trying to copy this theorem. I will open the page, just hold on a little bit. So I equals to a to b, open, phi is mapping from, this is not normal PDF, okay. So this phi is mapping from I to phi of I. Phi inverse is differentiable. Do you know all those functions? What is the name if its inverse is differentiable? It is not a probability question, but if you know, do you know? X probability X belongs to I is 1 and density exists. Then y equals to phi of x and G is the PDF of y on phi of. Okay, so let us see. This is what we know. We need to know the expression of G. Okay, so case by case. First, phi is a strictly increasing function, then phi is a strictly decreasing function. It is not at all a very difficult. So, case 1, let y equals to phi x when phi is a increasing function. So, we need to know the function g. Idea is same as we have already done, that you start with the CDF and then go wherever you want to go. So f y y, you can write that is probability capital Y less than equals to small y by definition. Okay, if it is so, then you can also write this thing that this is phi of x less than equals to small y, probability of that. Okay, then probability x less than equals to phi inverse small y. Okay, then what you will have? You will have integration a to phi inverse small y. So f x t dt, and now this is the situation. This is how you will get the CDF. Now, if you want to have the PDF from this CDF, what you need to do, that is G y is derivative of this CDF. So this is d dy integration a to phi inverse y f x t dt. Now you please tell me what will be the expression. X is defined on this interval a to b. Y is defined on, so, phi of it. So now you please tell me what will be the final expression here. If you are differentiating an integral where the variable what you are using for differentiation, it is on the range of the integral, then how will you do it?
We can use Newton-Leibniz to say that this is equal to fxt, fx
Hmm.
phi of phi inverse of y times
Right.
ddy of phi inverse of y.
Yeah. So this variable, whatever you are seeing in the range, here one side is constant, so you need not worry about that. But other side, that value will come in this uh, wherever x or in the expression of integrand, and then the rate of change of this function. So it will be f of x evaluated at phi inverse y, then dd y of phi inverse. Okay, so let it be in this form. We will come back to it. Then case 2. Okay, so y equals to phi x when phi is a decreasing function. Okay, now again routine job, but you have to be little bit careful. Same job. If y is probability y less than equals to small y, now it is probability that phi x less than equals to small y. Next step, you please tell me what I should write.
Probability x greater than equal to phi inverse y.
Okay, probability x greater than equals to phi inverse y. Correct. That means I can write, it is continuous. Okay, so no problem with that equality sign. 1 minus probability x less than equals to phi inverse y. Is it okay? Then I
Sir, it
can
should be
use,
less than, not less than equal to.
man, it is continuous.
Okay, sir.
All this is differentiable, all continuous. No trouble. Hmm. Acha. Then this quantity again I can express in this form. So this is again from a to phi inverse y ft dt. Okay. So again routine job. Gy is ddy fyy, which is, now you be little bit careful, ddy of 1 minus a to phi inverse y ft dt. Okay. 1, if you differentiate, it will be 0, no problem. Then it will come with negative sign. Then again the same thing will happen. Now let us consider f of x of phi inverse y, and uh, again if you differentiate it, you will get dd y of phi inverse y. Okay, now I want to consider to write this thing as like this and express it f of x phi inverse of y with this part minus 1 into dy of phi inverse of y. Now you see that phi is a decreasing function, phi inverse is also a decreasing function. So this derivative will be negative, only this part. This negative derivative with this negative sign. Can we write this thing as check from here to here is phi is decreasing, then phi inverse is also decreasing. So ddy of phi inverse y is less than 0. This is a decreasing function, negative function valued. So that quantity with -1 multiplied, I can write it is the magnitude only. Any query here? And as this is phi is increasing here, so this quantity is same is with its absolute value. So I have no trouble to write it. So is it okay? Any query? So the ultimate expression in any of these two, what you can see that this is the old PDF, f is the old PDF, and the new variable x, a new variable y is expressed in terms of or converted to the old variable, and it is the rate of change. Okay, so we can go for a new page 26. So the idea is this, that just a second. So gy is f of x of phi inverse y ddy phi inverse. Okay, so remember this thing. This is the old PDF. This is the old variable in terms of new. In terms of new, and this is the rate of change. And this is how you usually do the integration. Here, as it is a probability density function, it has to be non-negative.
Sir, what do you mean by old variable in terms of new? Like
So old variable means x. So
X, yes, sir.
y equals to phi x, x equals to phi inverse y. So this is old, and this y is new. Old variable in terms of new variable, and here you have the rate of change. Okay, so this thing is useful only, I mean, many cases you can use PDF and CDF, but especially when you don't have the closed form of CDF, this formula becomes most useful. So remark, when we don't have closed form of the CDF of x, then this formula is most useful. If it has, I mean, closed form of CDF, if you get for X, preferably go by the CDF. The chance of error is less. You will able to understand why I am saying this thing. Because many problem you will face when you want to use this kind of formula, you will not get one function which is strictly increasing or strictly decreasing over this range. Over the range of I, you may not get phi which is strictly increasing or strictly decreasing. So you have to split them over different parts where it is strictly increasing or strictly decreasing. Then part by part you have to take care, and then you have to merge it. So that is a little bit tricky job. But if you can go by CDF, my suggestion will be always go by CDF. The chance of error is much less. So by CDF I mean you start from this expression and in this way, and then derive. So that will be a safe path if possible. So let us see few
Sir?
examples. Yes, please.
Sir, if we are given PDF, then we can easily find the CDF, right? Then why to do all?
No, if you are given PDF, then your CDF need not have a closed form. Normal distribution CDF you may not be able to write in a closed form. You can write up to an integration, but closed form integration, as you can write the CDF of an exponential distribution, you will not be able to express the CDF of normal distribution.
So it will become it will tend to infinity or undefined, right?
What will tend to infinity?
If it is not in closed form.
Why? If an integration is not in a closed form, does it mean the integration will go to infinity? I mean closed form expression. So if you want to write this thing that e to the power minus half t square root 2 pi dt integration 0 to x. So capital this is, or say let us consider here fx. So can you have an expression in terms of x here?
No, sir.
That is what I am saying. Anyway, so let us do some exercise. It will be easy for you, not too difficult. First of all, you get the CDF. So do it the normal exercise 1. X follows normal, sorry, okay, so normal 0, 1. Y equals to mu plus sigma x. Okay, find the PDF of y. This is what you know and you can verify it immediately. Do it. So what do you need to know? So g of y, okay, g of y is, so first let us consider the inverse function. So here x equals to y minus mu by sigma, okay, as y equals to mu plus sigma x. So this is your phi of x and this is of phi inverse of y. And this is phi of x. It is straightforward one-to-one function, strictly increasing or strictly decreasing doesn't matter, depend. But here sigma is positive, so there is no trouble that sigma is greater than 0. So it will be always increasing function. So let us go for it. Y formula. F of x of this quantity, f of x of y minus mu by sigma, done, plus into absolute value ddy of y minus mu by sigma. As simple as that. So this quantity, you know the normal distribution PDF, e to the power minus half y minus mu by sigma whole square root 2 pi. Then derivative of this quantity 1 upon sigma. Sigma is positive. So as a consequence, you have this PDF, e to the power minus half y minus mu by sigma whole square sigma root 2, which is known to you. Okay. Now again another exercise you can do. Yes. So let x follows normal mu sigma square. Okay. And y equals to e to the power x. Find the PDF of y. Well, quickly. G y. It is also a strictly increasing function, right? Here you can also start from the CDF and you can go by that. There will be not much trouble, but let us use this formula. So first, what do you need to do? You need to know that y is strictly greater than 0 and x equals to log of y. Okay. So again, same story. It will be f of x of log of y into the derivative dy of log of y absolute. Is it okay? Now, what will be this thing? E to the power minus half log of y minus mu acha, whole divided by sigma square, this quantity square root 2 pi sigma. This is according to this PDF. This has happened. Now if you want to take the derivative, what will be the derivative of log of y with respect to y?
Sir, in the previous question, we were taking a normal of mu and sigma, and in this question, we are taking normal of mu and sigma square.
For what? What normal mu sigma and what is normal mu sigma square? Here also it has from normal 0 1 to normal mu sigma square we have transformed, right?
No, sir, mu sigma we have taken.
Why? Why? We have you done the class yesterday?
Okay, yes, sir, sorry, sir.
We specifically talked about it in the yesterday's class that sigma is the scale parameter, sigma square is the variance. So here sigma is the scale parameter. When we write as normal mu sigma square. Okay.
Sir, I didn't get why the sigma comes in denominator here.
Yes, sir. It should be
Here
y.
you see that this is the definite distribution. So y follows normal mu sigma square, right? So this is the PDF of normal mu sigma square. I am following that PDF only. Here in place of y, we are writing log of y because x is following normal mu sigma square.
But from the above formula, if we directly take, okay, sir.
Above formula, this thing came from the PDF of normal 0 1.
Yes,
So
sir.
sigma was 1 here. And this came from this derivative. Now this whole is applicable directly here. So sigma is here, root 2 pi is here, everything as it is here. Now the derivative we have to multiply. What it should be?
1 by y.
1 by okay. So this is the PDF. This distribution is known as log normal distribution.
Sir, is taking mod important because y is already
Y
greater
is positive, not important, but just for as I am started with this mod sign, I have followed.
than okay, sir.
So this y is said to follow here log normal mu sigma square. Okay, or when something is said to follow log normal mu sigma square, if log of y, that eventually log of y is following normal mu sigma square. If log of y follows normal mu sigma square, then we say y is following normal mu sigma square. Quickly, can you tell me what will be the expectation of y?
One.
No. X is following normal mu sigma square. Y is e to the power x. I am looking for the expectation of e to the power x.
So e to the power mu x plus half sigma square x square.
Half sigma square.
X square.
How? You have taken the expectation, right? X, how x will come after taking the
Sir, e to
So
the power mu plus sigma square by 2.
e to the power mu plus sigma square by 2. So you note this thing that this is uh, mm, expectation of e to the power x, which is eventually mxt evaluated at t equals to 1. So e to the power mu t plus half sigma square t square at t equals to 1. So e to the power mu plus sigma square by 2. So this is the moment generating function evaluated at 1, t equals to 1. Students often do the mistake in usually interviews that if you ask what is the expectation of e to the power x, they just say it is e to the power mu. That is not correct. So be careful, and it is very easy if you know the moment generating function. It directly comes from the moment generating function. Just put t equals to 1, you will get the answer. Okay. Now I ask you to do okay, so few more exercise, similar type. So these are homework that let x by lambda to the power k is following exponential 1. Okay. So if this random variable follows exponential 1, then find the distribution of x, and if whatever distribution you will get, x is said to follow Weibull distribution. And it is also a waiting time distribution. Okay. Whatever PDF you will get, that is known as the Weibull distribution. And then homework 2, another interesting homework is this. So say for example, okay, I have given it somewhere, Pareto this quantity 96, that 1 minus lambda by x whole to the power k, 1 minus lambda by x whole to the power k is following uniform 0 1. Okay.
Sir, exponential of 1 x by lambda whole to the power k follows exponential of 1 means it is e to the power x. Right?
Oh my goodness. I mean, how long you are missing the class, man? This is
Yes, sir,
the
it is the distribution. I
yeah,
forgot.
the distribution. So this is the parameter of the distribution. So
Yes.
specifically this thing I told, that when we say that some random variable is following exp1, that means you need to consider the CDF1 minus e to the power minus lambda t as the CDF, or lambda into e to the power minus t lambda t as the PDF. This is what you need to consider. So this quantity will come in place of t. This is the thing will have to be written in place of t, and then you need to take the derivative. You will get the distribution of x or PDF of x. A similar situation, that this quantity is following uniform 0 1, then find the distribution. So this is say phi of x. This is say phi of x. Phi of x distribution you need to know, then phi inverse of that variable, the distribution you need to find of x. So here this x is said to follow Pareto distribution. And this is often used to model the income distribution. For household income, the distribution of income over an region. So this kind of thing, and you will come up with this that so here you can see that f of x, you can write 1 minus lambda by x whole to the power k, 0 when k is positive and x is greater than lambda. Otherwise it will not hold. X is greater than lambda, then only 0 otherwise. So these are the two homeworks I am leaving. Now another interesting exercise that we can do in this connection is this one. That say let x follows normal 0 1 and y equals to x square. Find the PDF of y. So how do you do that? Remember, here x square is not one-to-one function. So it is not even monotonic function. So what will you do? This is for waiting.
So solve separately for x greater than 0 and x less than 0.
After that,
Means we might get similar function with plus minus sign difference.
then
We can take mod at the end. I'm not solved, but I think it will be something similar to that.
okay. So that part you will do, but as a homework, let us do by in usual method that probability. So f y y probability y less than equals to small y when y is positive. Definitely y is positive. So this is probability x square less than equals to y. So that is probability minus root y x root y. Okay. Then what you can do, immediately you can write it in this form, minus root y to plus root y e to the power minus half x square root 2 pi dx. Okay, but here we have an advantage that this function is an even function. Integrand is an even function. So this will become 2 times 0 to root y e to the power minus half x square by root 2 pi dx. So this is the PDF, sorry, CDF. Now from here, if you want to get the PDF, so FYY is DDY of FYY So you have to do the derivative, again the same problem, 2 times to root y e to the power minus half x square root 2 pi dx. So what will be the formula? Finally, 2 will be there. Then
2 e to the power minus y by 2
e to the power
divided by
minus y by 2
divided by root 2 pi
2 pi
times 1 by 2 root y.
You have to take the derivative, right, of this quantity.
Yes, sir.
So what will be that one? Root y, and half will also come, right?
Yes, sir. 1 by 2 will
1 by 2 will also. Okay, so let us see, can we arrange this thing little bit? So can we write this thing as y to the power half minus 1, then e to the power minus half into y, then this 2 will cancel, and we will be left with 1 by root 2. So 1 by root 2 we can write as half to the power half, and root pi we can write as gamma half. Is it okay? Is it okay?
Yes, sir.
So can you identify the distribution now in terms of gamma? What will be the parameters? In terms of gamma distribution, what will be the parameter?
Gamma half, comma half.
Gamma half, comma half, correct. So y is following gamma half, comma half. So this half is for alpha, this half is for lambda. This is shape and this is rate. Okay. Now we are going to define a very important distribution. Or we are just going to give the name that this is the definition in this way, that if x1, x2, xk are IID normal 0 6 normal 0 1, then sum over xi square I running from 1 to k is said to follow chi-square distribution with degree of freedom equals to k. So degree of freedom. So degree of freedom means as many free variables are there. If you want to know more details, then you have to come to my regression course. There I will even give you more generalized definition of chi-square distribution and its entire application to regression and ANOVA. But for the time being, here degrees of freedom will be k, because here you have k IID random variables and they all are free. There is no dependency involved among them. Acha. So for this one, what will be the distribution of y in terms of chi-square? What will be the distribution of y if I say this is known as the chi-square distribution? CHI chi-square.
df equal to 1.
df equal to 1, degree of freedom will be 1. So this is equivalent to chi-square with 1 degree of freedom. Okay. Now, can you tell me what will be the gamma equivalent of it? Gamma equivalent expression of chi-square k. Its gamma equivalent?
Gamma k by 2 comma half.
Gamma k by 2 comma. This will be gamma k by 2 comma half. Because each individual xi square is following gamma half half. And you have the additive property of gamma that you have studied in the previous lecture. So all alphas will be added, k alphas will be added, each alpha is taking value half. So gamma k by 2 comma half. Now quickly tell me what will be the expectation of chi-square k and what will be the variance of chi-square? One line job now.
But 2 alpha.
First one?
So k.
K. So alpha by lambda, which is k, and alpha by lambda square, which is
2k.
2k. Bas, done. If you want to write its density function and then go for the calculation, you can do it, but well, that will take. But now this is your homework that some of our student has told that you can do it part by part, this job. So it is homework that verify using the theorem. So you first take the part 0 to minus infinity to 0 when it is strictly decreasing. Then you take the part 0 to infinity when it is strictly increasing. Come up with the same expression, sum them up, and then you check whether you are getting the same expression or not. Okay. So you will get it, but you verify this same thing using the theorem that we have just learned today. Okay, so this is a chi-square distribution. So where you can think that this can be used? Where you can think that it can be used? You will come across this distribution. I mean, how many times in your life you don't know, if you are really working in statistics or data analysis. It has a very natural application. From this expression, can you say something? Any clue? If you consider that x1, x2, xk is a vector, then sum over xi square is x transpose x. And what does it represent? What is the meaning of this expression?
The square of the modulus of the vector.
Yes, of course. If you have done square, you need not take the modulus. But anyway, you are right. So what is it for a vector? If this is a vector, then what is this quantity for it?
Distance from origin.
Yes, it is the Euclidean distance from origin, or the square of the length, right? So it is, its application is distance measure. So chi-square is heavily used for distance, the statistics when you are measuring the distance. You have two random vectors, you are interested to take their distance measure, then chi-square distribution very often comes when the vectors are following normal distribution. Very often you will come across this thing. And chi-square distribution is one of the common thing. Okay. Now another application let us go for. Okay, so we can do few works also, but anyway, let us do some applications also. Okay, so now this is a separate story from chi-square. We will come back to it. Suppose you have a situation like this, that there is a circle and here is a line and here is a top point. Okay, and you can think that there is a line is also going there, imaginary. Then there is a source of light is here, a source of light is here, and that one light ray is coming, it is cutting a point and the shadow of that point is falling on this line. Okay, here if the source is coming in this direction, then the shadow is falling in this direction. If the source is coming in this direction, then the shadow is falling in this direction. So each of the shadow of the periphery of the circle is falling on this line. Okay, now this light source, angle of the light source can vary. So theta can vary uniformly from -π/2 2 pi by 2. Okay, if it is so, then if I define in this way, say this is 0 and this length is y, consider this height is 1. Can you find the distribution of y? So it is something you may also assume that there is a sprayer which will maybe spraying pesticide from a plane or some at the top angle, and it can rotate from minus pi by 2 to plus pi by 2, and it is spraying pesticide on the field. So same thing it is happening, and the rotation angle can vary from minus pi by 2 to plus pi by 2. So find the distribution of y, the range it will be able to cover. Whatever geometrically we have drawn here, this kind of thing, this projection of all these points on this line from a circle to this thing, when in mathematics and geometry or complex analysis it is studied, it is known as the stereographic projection. So it has a very huge application in complex analysis. And I hope you have heard the name of Riemann, because you have learned the integration due to him. And this idea of stereographic projection and connection with complex numbers, all is due to him again. And this is in 2 dimension. In complex analysis, it will come in 3 dimension. But anyway, just tell me what.
Sir, PDF will be 1 upon pi times under root 1 plus y square.
1 upon pi times 100. So that is correct, because this is very easy to get. So f y equals to probability y less than equals to small y. So again, you can have probability tan theta less than equals to y, and probability theta less than equals to tan inverse y, and then theta running from minus pi to plus pi. So tan inverse y minus of minus pi by 2 and pi by 2 minus of minus pi by 2 from the definition of uniform disk. So this quantity fy y is eventually coming as half time plus 1 by pi tan inverse y. So small fy y is 1 upon pi 1 plus y square. Okay, and y belongs to the entire real line. What will be the expectation of y?
Zero.
Any other alternative? कुछ बदला नहीं, तुम्हारे सीनियर भी यही गलती किए हैं, तुम भी यही कर रहे हो। हर साल एक ही प्रॉब्लम।
Sir, not defined.
Sir, is it undefined?
It is not defined. If you go, it does not exist. Already we have given this as mod of x, mod of y, fy dy minus infinity to plus infinity will go to infinity. None of its moments exist. But interestingly, the density will look similar to normal, but it has a very thick tail. The tail part is not as thin as normal distribution. So if this is Cauchy, oh sorry, I will tell you the name. This name of the distribution is Cauchy, and this is normal. So blue one is normal 0, 1, and the black one is say called, this is known as the Cauchy 0, 1. So this distribution is known as the Cauchy 0, 1 distribution. This distribution of y is said to follow Cauchy distribution. And again, there will be some connection between Cauchy and normal that we will be able to prove after few lectures. This thing you will be able to, we will prove it, not now, that x1, x2 IID normal 0, 1, then x1 by x2 follows Cauchy 0, 1. This we will prove later on. There is a connection between Cauchy and normal. We will prove it that x1, x2 IID normal 0, 1, then we can show that x1 by x2 follows Cauchy 0. The thing is that the level of contact this asymptotic part of the normal distribution have with the x-axis, the level of contact this one, the Cauchy, will that much don't have. That's why the thick tail distribution. This thick tail distribution often comes in your stock market data. Okay, so application is stock market data. In many situations, thick tail distribution or heavy tail distribution, people say that is coming in stock market data, and dealing with them is really challenging because the moment doesn't exist. If the moment exists, identifying the distribution, doing some work with it is very easy. But when the moment doesn't exist, everything you need to do in terms of the quantile or percentile, so life is more challenging there. Okay, so now let me give the concluding example and the thing. Before that, let me define a few distributions which we will not study now. We may study after your second class test. So another so I'm just giving the names and the definitions. We will study later on. So T distribution, all will be hugely applicable in statistics part. So if x follows, or okay, so normal 0, 1, y follows chi-square with k degrees of freedom and they are independent, then W equals to x divided by square root of y divided by its own degree of freedom is said to follow T distribution with k degrees of freedom. So this is df. Same df of chi-square will come here. This is one thing. Another is F distribution. So application will be testing of mean when variance unknown, then testing of regression coefficient, All those things can be done under normality. All those things, even the correlation coefficient can be checked. That thing we will come. So this is the huge application. No other alternative. So F distribution, something similar. If x follows chi-square with m degrees of freedom and y follows chi-square with n degrees of freedom, and they are independent. Independent is important. Without independent, it will not hold. Then W equals to x divided by its own degree of freedom, y divided by its own degree of freedom, is said to follow f with it has 2 degrees of freedom, m and n. Okay, so the application is the comparison of normal variances ANOVA, analysis of variance, so if you want to study that what are the different sources of variation in your data and which one is important, which one not important, you need to do a testing with respect to AFP distribution. And the most important thing is the multiple hypothesis testing. Multiple So in all those cases, you need to use F distribution. We will study it later on. Chi-square, T and F. So usually this chi-square T and F are known as sampling distributions. Because all these statistics usually come from the data-driven expressions. Just a name. And they come from the sampling. We will talk about this thing later, not now. Okay, so now the result. Which is the source and which is the ultimate. Let x follows some CDF f and x is a continuous valued random variable. Okay. So if this, and I am defining y equals to, so we can write this thing as fx. Y is this. Then find the distribution of y. I have not specified any specific distribution. It could be any continuous distribution, doesn't matter. Fx is strictly monotonically increasing and differentiable at the same time. So what will happen? Gy, what will be the range of y?
0 to 1.
0 to 1 because it is probability.
Sir, will
So
it be uniform distribution?
yes, of course, it will be uniform distribution. Parameter? You have, whenever you say some distribution, you have to talk about its parameter. So this is probability y less than equals to small y, which is probability f x x less than equals to small y, which is probability x less than equals to x, sorry, f x x inverse small y. Now you know f is following, x is following with this CDF. So this is fx of fx inverse of small y, which is y. Now tell me, what will be the distribution?
Uniform.
Uniform. Parameter?
So 0 to 1.
0 to 1. This is okay. So 1 when y greater than 1 and 0 when y. So y follows uniform 0 1. So we have returned from where we have started with. And this is the key thing of your computer simulation. You start with uniform 0 1, you invert it with any possible CDF function, you will get a random variable which will follow that CDF. So you start with any uniform 0 1, you invert that thing number with respect to any possible, admissible CDF function, you will get a random variable which is following that CDF. So that is the, so you generate from uniform 0 1, which computer in a pseudo sense can do, then invert it with respect to a CDF, the new random variable, the new variable will follow that CDF. And that distribution will be characterized by which function. So eventually this is the thing. If you have a CDF, any arbitrary CDF you choose, then you generate from uniform 0 to 1. You generate from here, suppose this value you have got, you take its inverse x, and if this is f, then x will follow. This is the whole idea, and this is the idea of data generation from computer. So if you want to summarize the entire thing that we have done, you can see that we have started with uniform 0 1, then from here one splitting we have done, say I should do in this way. Okay, so discrete uniform Achha. As a special case of that, we have got Bernoulli, or maybe Bernoulli. From Bernoulli, we have got binomial. From binomial, we have got Poisson. Again, from Bernoulli, we have got geometric. From geometric, we have got negative binomial. Anything else we have done? Maybe not. Okay, then we went for the continuous case. First, we came to exponential. Then sum of exponential is gamma. Acha. Then ratio of gamma, this is sum, properly taken. This is beta. Okay. Then gamma beta. Okay, so another separate story comes from uniform, which takes us to normal. From normal to chi-square, and chi-square and gamma are equivalent. Acha, from normal we have got log normal. Acha. And what else? Exponential, gamma, beta, log normal. Anything we are missing that we have done?
Hypergeometric.
Hypergeometric we have not done in this. Hypergeometric is a separate story which we have not done in this way, but still we can go for it. That there is a and whatever probability you can assign. So from discrete uniform with lots of effort we can go for hypergeometric. Where will you place the Pareto and Weibull? Pareto, Weibull. From exponential we can from uniform directly you can go to Pareto, and exponential you can go for Weibull, and from uniform directly you can go for Pareto. It will not be a problem. So this is the ultimate thing that we can have in our mind, and again whatever you have seen, that all this uniform thing, whatever you have seen, they can again go back to uniform, just the result you have seen. So this is the key idea, that we can go from one distribution to another, and they are so interrelated. They are not separate stories. Even from exponential you can go to geometric. That also you have seen. So from exponential you can go to geometric. Even from geometric you can go to exponential, but I cannot do that proof in your course. So all this stuff you can have in a very nice way. So they are not separate entities. That is what I want to say, that they are not separate entities. They are interlinked, and the origin is always uniform, and under certain conditions you can go back to uniform. So that is the whole idea of studying all these spatial distribution. Oh, Cauchy. Again, uniform to Cauchy or normal to Cauchy. So from uniform or normal, both way you can come to Cauchy. And that helps us for the flourishment of all these ideas, this computer generated simulation and whatever data data analysis, data or not, the data science we are doing nowadays. That is because of this computer facility, and computer facility is coming through this uniform distribution, because computer cannot generate random number. It comes through an algorithm, and whatever is coming through an algorithm, it cannot be a random number. So what is happening there, we the search space or they usually use a formula something like this: xn plus 1 equals to a. This is a very simple most one. There could be many other. Plus b plus xn modulo maybe say 10 2 to the power whatever bit system you have, 32 bit or 64 bit, something like that. So in this recursion, a chain is going on, and the outcome xn you are getting from there, that appears as a uniform distribution over this range. So xn plus 1 divided by this, say 2 to the power 32, or this is a large number. Okay, so x n plus 1 by a very large number. This is supposed to follow uniform 0 1, and computer can produce this thing. Yeah, so pseudo random number which is following uniform 0 1. This much facility we are taking from computer, rest of the thing are from our statistical knowledge. So all those, there are some transformation which is converting this uniform to any of these random variable, and through software by which you are getting all this computer generated data. Okay, so this is the core background of how statistics and computer works together. Any query? So what can I do now? All necessary thing I have done for this course. Only few thing I have to tell you related to some hazard function and reliability. Okay, so let us study few problems. Let us do some problems. We have enough time. Any query? Any question? Okay, we can see the diagrams first before we go anywhere. We will also have a logical break with it. So here, Bernoulli distribution with this 0.3 and 0.7, 0.3 with for probability 0 and 0.7 with probability 1. So 0 are the small dots and 0.7 is the big bars. So if you, there are 100 samples, and if you see the histogram, it's 30%, 70% approximately. Now, if you go for 1000 samples, you can make a transformation from Bernoulli to -1 to +1. How can you do that? X is following Bernoulli. now you want to convert it -1 and +1. How can you do that? What will be the transformation? If it is 0, take it to -1. If it is 1, take it to 1.
2x minus 1.
X minus 1. How?
So
Then
2x minus 1.
2x minus 1. Okay. So 2x minus 1 will work for it. And that thing can be able to model so many interesting things. Okay. So say for example, if I say now that if I flip a coin, if it is head, you will give me 1 rupee. If it is tail, I will give you 1 rupee. So this is a win and loss situation, and the amount is associated with it. And not only that, you can model that kind of thing with, say, this situation, that suppose there is a particle that randomly either can take +1 move or -1 move. Okay. So in this way, it can move on the integer grid points of real axis. So first I win, then I win, then I lose, then I lose, then I again lose, I again lose, then I win, then maybe I win, then maybe I lose, then again I lose, then again I lose, then maybe I win. So in this way, the transition can happen, and it is called a random walk on the integers. Okay. Same thing, and it can happen with equal probability, with probability half and half. It can happen with unequal probability. So it can be shown in probability that if it is not half, definitely if I start from 0, definitely I will move away from 0. But with probability half, it can be shown with probability 1, I will be eventually returned to origin. So can you tell me that whether in odd number of transition, may I be able to return to origin? Is it possible?
No, sir.
It is
No,
not
sir.
possible. So you need an even number of transition to return to the origin from where we have started. Not only this, you can even extend it for two-dimensional grid. So for simplicity, you can think that equal probability 1/4, this direction, this direction, this direction, this direction. You can go. Okay. And if the probability is 1/4, then with probability 1, you will eventually come back to the origin. Now, if you go for 3 dimension, so this. So this way, this way, this way, this way. So what will be the equal probability for each of the direction?
1/6.
1/6, but no return. Return not guaranteed. Start from origin, equal probability, return is not guaranteed. So this one, return ensured. For this one also, return ensured. And here, return not ensured. It can be proved. So this is simple symmetric random walk in integer grid in so it is in Z2 and it is in Z3.
Sir, why is return not ensured?
Oh, it can be proved. You need a
Just go in the opposite direction as we go.
yes, and not only 3 dimension onward, wherever you go, return is not guaranteed. That proof can be done, and that proof is not so trivial proof, but it can be done.
So what do you mean by return guaranteed?
Return guarantee means with probability 1, I will come back to the origin from where I have started with. Is it okay? From which point I have started my journey, eventually I will come back to it in long run. With probability 1, I will come back. But here it can be shown with probability 1, we will not come back. So this is a very interesting thing, and this is the building block of many sophisticated models, which is used not only in finance, it is used in physics and many other aspects of modeling of time series. So this is the one of the very fundamental thing, and all comes from this plus minus 1 idea. So that is what I have done here with plus and minus 1. Again, it is 30-70 allocation here. Achha. Then cumulative sum. If you do the cumulative sum, then again you can see that if it is highly weighted to 1, then it will be gradually increasing, and from here you can see that there is a chance that we will be deviating, that is ensured. But if the probability is half and half, it will be fluctuating around 0. It will not go away from 0. If it is probability is half and half, so this is the path of a random walk. It tells you at what location you are. So you will not going too much far away from 0. Okay, so and here you can see that initially there will be fluctuation, but here it gets stuck with certain number, which is 0.7 into 1 plus minus 1 into 0.3. So 0.4 will be the value here. But if you go by half and half, you will stick to 0. Eventually you will converge to 0. So this red dot line is the 0 line. So eventually it will converge to 0. So that is what it is trying to say. Okay, so discrete uniform, throw of dice, no problem. But you can assign any number for these cells. You can assign even not number to these cells. So you can go for say people with eye color brown, blue, black, something like that, and then also you can go for it. Categorical data. Binomial, nothing more to say. With different parameter values, red one as the true values and the green one are the simulated values. Already we have seen. Then binomial, I have used two different generation. One is software generation, another is data driven generation that we explained in our method, that go from uniform to Bernoulli and Bernoulli to binomial. So two generations are given and they are compared. Similarly, geometric, it has an exponential decay trend, and you have seen its connection with exponential. Again, two generations from geometric. Negative binomial, it is the sum of geometric that you know. Okay. Again, two generations of negative binomial. Poisson, already we have talked about it. But again, this thing we have talked about when we have introduced Poisson, that whether n into Pn is going to lambda, then you are eventually not be able to distinguish between Poisson and binomial there in that situation. Okay, multinomial means it is just a generalization of discrete uniform. The probability are not same for all of the cells. It can be different probability, total probability 1. That's it. It is a very simple structure. but it as because of this flexibility, it has a huge application. Okay, continuous, discrete uniform that we have talked about, uniform 0, 1. Then with transformation, you can go for uniform A to B, which definitely will not look like uniform
Sir,
0,
can
1.
you please show again that multinomial one?
Yes.
So,
Yeah.
sir, what are the axes in multinomial? The
So
axes, could that be x2 also?
No. This one, x1 is the numbers, or you can have the categories, and y direction, the probability or the proportion, it is taking value 1, proportion, it is taking value 2, and so on and so forth.
Oh, okay.
So I have generated here 1000 sample from 5 categories with probability 0.2, 0.5, and rest all are 1. So I have got this frequency or proportional frequency, and the proportional frequencies are plotted in green line, and these probabilities are plotted in red dots. Okay.
Yes, sir.
Okay, so now exponential lambda, nothing special about it, we have done lots of work on it. Then gamma, it is a sum of exponential. Now normal, well, when we will study bivariate random variable, we will talk about bivariate normal, and there you will see a nice connection with that why root 2 pi is there. The circular structure you will be able to see there. Okay, then with the transformation of location and scale change, you have different normal distributions. Okay, so here it is chi-square. Chi-square, how much degrees of freedom we have? 5 degrees of freedom. Chi-square, you can see that the peak is very nearby 5. So it is 5 degrees of freedom, and the expected value is 5. Okay. Here are different chi-square distributions. So if degrees of freedom is 1, then it is gamma half. Okay. If degrees of freedom is 2, then what it will be?
Gamma 1 half.
Gamma 1 half. If df is 2, then gamma 1 half, and gamma 1 half means chi-square 2 is equivalent to gamma 1 half, and gamma 1 half is equivalent to exponential gamma 1 lambda, right? So it will be exponential half, and exponential half will have PDF. What will be the PDF?
1 minus e power minus t by 2.
So half, it is half, so e to the power minus x by 2. So at when it is going to 0, it should start from half. So that is the thing you can see, that with degree of freedom 2, the green line, it starts from half and it is exponentially distributed. Same thing as the exponential distribution. So it is exponential half eventually. So all these things you need to remember, and the connections also. Okay, T distribution that we have defined. Here I have plotted T distribution with different degrees of freedom, and eventually the T1, T distribution with 1, by definition it will become Cauchy. Okay, so here we have written this thing, when we have talked about Cauchy, there is another characterization that also x1 divided by mod x2 will also follow Cauchy. Proof can be done, a similar proof that x1 divided by mod of x2 will follow Cauchy. Now if you go by this definition of Cauchy, and if you see this definition of T, so x following normal 0 1 square root of chi-square with 1 degree of freedom. Chi-square with 1 degree of freedom, you can say it is normal square then square root divided by 1. So that will be eventually the same thing, x by mod of x1 by a mod of x2, both are following IID normal, and then it will become T distribution with 1 degrees of freedom, and that is the same thing. So T1 is Cauchy 0 1. Okay. T1 is a Cauchy 0 1. So if somebody asks you that what is the mean of cos T1, don't say it is something 0. It is Cauchy 0 1 and the mean doesn't exist. But here you see this thing that T1, that is the red one, it has the more thicker tail than compared to the other T distribution, and the dotted line, which is the PDF of normal 0 1. So as the degree of freedom of T increases gradually, more and more and more, if you increase, if the degree of freedom goes to infinity, then it converges to normal distribution. So you can see that with 10 this much of gap, if you increase to 100 and 1000 in that way, then it will almost overlap with this dotted line. And the probability gap will be maybe say around up to 3 or 4 decimal place will be same if you go for maybe let's say 500 degrees of freedom or 1000 degrees of freedom. Okay. So often for large sample situation, instead of doing t-test, we perform the normal test, because we need not go for that. Normal table is available. The data or the quantile values from normal distribution is easy to get. Okay, so log normal, from normal you can transform it and you can get the log normal, no problem. Cauchy. So here is this is not so good looking, but the way we have just the circle I have not drawn here, but the way we have talked about the data, this is the generation, that here is the circle, this is the source of light, and the light rays are falling on this line and the distribution is generating. So if you increase the number of samples, you will get a very smooth curve, but it will have a very long and flat tail. Okay, so this is how it works. Anything else? I think my all done. So we have 5 minutes time. Any query you have? Otherwise, in the next set, yes, bolo.
Sir, in the Cauchy part.
Yes. Well, Cauchy. Where is Cauchy?
Sir, in the PDF itself.
Oh, for
the
PDF.
distribution.
Yeah, here.
Yes, sir. Sir, here we are incidenting light on a plane surface. So,
not
sir,
plane surface. Here it is not plane surface. It is a line.
Yes,
you
sir.
are saying a vertical cross section like that. One light source on one line. So you can say that like this. This is the light source and this is only falling on this line.
Okay, sir. So, okay. Sir, shouldn't it be symmetrical?
Symmetric. It is, yeah. If you so if you Cauchy distribution, you see that I have drawn it. It is symmetric. Here I have. Here I have very small number of data, and because of some plotting problem, it is coming asymmetric. But because of sample. There are samples drawn, so you are getting this asymmetry. Otherwise, if you just see the density, so this one, this red one is a symmetric distribution, right? Cauchy 01 is a symmetric distribution. If you plot the PDF, theoretical PDF, it is symmetric. You are right.
Okay, sir.
But as you have drawn sample, it may not reflect that thing always. Is it okay?
Yes, sir.
Hello? Hello?
Yes, sir. It is okay. Hello?
Yeah. So if you go by the theoretical PDF, it is definitely symmetric, and from the expression you can see, and from the graph also you can see. But here you can see that although it is, look here, the this curve is drawn. That curve is drawn based on the PDF. But here the data, you can see that here this side has small data, less number of data points, but this side it has gone up to maybe say 7. Here it has not gone up to -7. So although it is drawn from normal distribution, it is symmetric. But how the data will behave, it should resemble with the PDF, but it will not be, never be exact the PDF. PDF, CDF, all those things are, something which is there, but we have never touched it. What is the data is the manifestation of this PDF and CDF. So whatever we know through data, and there is something sitting there which is assumed to generate all those number in nature. Okay. And but with data you cannot transfer the information. So this entire language of mathematics or statistics, whatever you say, it is only to facilitate you that what somebody can do, you will also be able to implement that thing. That's why all this mathematics is needed. Otherwise, I can tell you that this is the data, in that way you do its processing, in that way you do it, but that will, following that instruction is more cumbersome than if I say that, well, if the data follows normal distribution, you do this. Then you have a precise prescription that, well, if I see this kind of feature in my data, I will do this. An entire mathematics language is for this purpose. Say, for example, if you want to say that if you have a square, then the area of the or the length along the diagonal will be square root times of the side. Suppose you don't have the idea of number, how will you pass that information? It's a very simple thing you have taken for granted. How will you pass this information when you have no idea of number? Suppose you don't know anything about number. You have a square set and you want to pass this information to your friend that the length of the diagonal will be square root times of the length of the side. You can see that from just to infer, pass this information, not only any number you need a irrational number, which is not common to observe in nature. So you just go for counting, and if you have just a you are taking the measurement with some string which has no labeling, then coming up with the idea of a irrational number is a very challenging task, but it has opened up so many things. Okay, in next week we will study a little bit about reliability application of all this stuff. in your, I mean, as an application of whatever we have studied in reliability. That thing we will study in the next week. Okay, thank you. See you.
Thank you, sir.
Thank you, sir.
Yeah,
Thank you, sir.
thank you.